In this video, I'm going to focus a bit more on the fact that the gradient changes and then the implications of the fact that the gradient changes. What does that mean for the way we express the gradient or the way that we actually calculate the gradient if it's going to keep changing? You can see from the diagram here, I've got the parabola and I've drawn a tangent at x is equal to -1. You can see that, and you've heard me say previously, our tangent represents the gradient at a point. So this red line is representing the gradient at x is -1. I could do my little calculation for the gradient at that particular point using rise over run and get that it's -3, as you can see here. And that is supported by the fact that the red line is sloping down. It's got a negative gradient. I then have also drawn over here, same graph, although it's a different scale, the y equals x squared, still the parabola. I've drawn it like this because I want to investigate what's happening over here at x is equal to 2. I've drawn my tangent at x is equal to 2, and I'm investigating the rise over the run of my tangent there, and you can see that has turned out to be 8 on 2, which is 4. Our math supports the fact that that the gradient is changing along the curve. What does that actually mean then for the derivative, which is going to be finding the gradient along the curve? The fact that it is changing, we can see from the graph that at x is -1 and 2 on the parabola that the gradient it's changed. What does it mean if the gradient is changing? It means that if we want to express the gradient, then our expression for the gradient must contain x. So therein lies the first of our major changes. So the gradient is no longer a constant number. The gradient may be expressed or must be expressed involving an x. So we may now see things like the gradient is equal to x plus 5, or the gradient is equal to 3x, or that the gradient is equal to x squared. Now, we've got names for these. We call these things functions. That's a function in x, that's a function in x, and that's a function in x. What we're going to see is that we will develop gradient functions. And like with all functions, you then could be asked to graph them. So you will be graphing the function of the gradient. So this is one of the first significant differences about the gradient that you need to be aware of, and it will help you to understand when you learn the process for differentiating. It will help you to understand what the answer you get to your process is representing. So just going back to these examples, if we knew that the gradient was this function x plus 5, we wouldn't have any trouble graphing that, x plus 5. We know that x plus 5 would be a straight line, positive gradient, cutting the y-axis at 5. We could draw that gradient function. Likewise, if we knew that the gradient was 3x, again, it's another nice straight line, we would draw that gradient function, passes through the origin, positive gradient again, straight line. If we knew that the gradient was y is x, that the gradient function was x squared, we would be drawing a parabola. However, the more common questions that you're going to find, especially here in the beginning, is you're going to be asked to draw the gradient function and you won't be given the function. You won't actually know whether you're drawing a straight line or a parabola. So the only way that we can draw a gradient function in that case is to study the gradient of the curve. We've got to study the gradient of the curve and actually record if it's positive, if the gradient is negative, if the gradient is zero, and then use, as you can see, I've got a little table here, and all I'm going to be recording in it is my gradient positive, negative, zero at these particular points? And we'll then use that to construct. It'll be a very, well, it won't be an exact gradient function because all we'll have is whether it's positive or negative. Values, we won't know the exact size of it being positive or negative. Looking at this function, what an helpful thing to do is to just think about, if we were to draw tangents, just think about whether the gradient would be positive, negative, or zero, and actually put that here on this graph. So if I'm here at this point, I can see, yes, the gradient would be positive. And where am I here? I'm somewhere, x is somewhere between -2 and -3. So try to keep tabs also on where you are in terms of x. Here at x is equal to -2, when x is -2, still the gradient would be a positive. And sometimes I draw these as a bit bigger positive and then a smaller positive because the value is getting a little bit smaller. As x is moving closer here to this particular point, the gradient is less steep, it is less positive, and if I can possibly draw an even smaller positive, then I will. Right here, when x is this value, and that's just a little bit less than -1, the gradient will be 0, because if I draw a tangent at that point, then it's horizontal, which means it has 0 gradient. Once I start to move up here, getting towards -1 and closer to x is 0, you can see that the gradients are now going negative. So a little bit negative, a little bit more negative, not so negative, until I'm right back to here, and the gradient also would be 0. But thereafter, the gradient becomes a little bit positive, more positive, and much more positive. I'm going to now take those positive, negatives, and zeros and put them here into this table. So we said at x is -2, the gradient was still positive, but it was not as positive as it is down here. It was not as big a positive value. It's getting less positive. The actual x value here is -1.3, and we saw that the gradient was 0 there. At -1, it's a little bit positive. At 0, x is 0, the gradient went back to being 0, and at x is 1, it was a little bit positive, and 2, it's getting bigger positive. Now, this is all we have at this stage for drawing the function of the gradient. We can only indicate on our gradient function graph whether we're positive or whether it should be 0 or whether it should be negative below the axis. So that's what we're going to do down here. So to actually do that, you can follow these steps. And the easiest points to plot are the points on the x-axis where the gradient is 0. So if we're drawing the gradient now, so this is measuring the gradient. And notice I haven't put any numbers on it because I actually don't know the exact size. I know that at times it has to be positive and at times it has to be negative. The easiest points to plot are the times when it has to be 0. So it's saying when x is negative 1.3, the gradient is a 0. So we know it will definitely go through that point. We also know when x is 0, the gradient will be 0. So it'll go through that point. At x values less than negative 1.3, we can see the gradient has to be positive. And again, positive just means above the axis. For everything below there, the gradient was positive. And that's about the best I can do. Between x is negative 1.3 and 0, negative 1.3 and 0, in between here, the gradients were all negative. So I know that the gradients went negative, but then they came back and was 0. So I've got to go down into the negative region, but actually get back to 0 at x is equal to 0. Thereafter, the gradients go positive. So we indicate that by putting our graph above the x-axis in the positive region. And that is as good as we can do for the gradient function, graphing the gradient function for now, because we don't actually you can see it's a parabola. And as we move through the chapter, you'll see actually why it's a parabola. If you look back at the original function was a cubic, and its gradient function is a parabola. Try to just hold on to that. So original function was some cubic. The gradient function is some quadratic. Yeah, there's a connection between that, and we'll come across the exact association later in the chapter.